We'll start in 1 minute. Okay, today we'll be in section 7.5, solve applications with rational expressions. So some of these will be sort of challenging. Others are easier. This first one isn't too bad. This one is easy enough that you could just do this in your head, but one of the goals is to learn how to set up an equation with the given information and then afterwards solve the equation. This particular problem is an example of a proportion. So I'll just note the word proportion and then expound on that a little bit later. So we could say, based on the first part or the first sentence, 13 milligrams of medicine is to 9 pounds of a child's weight. As we'll fill in the next part based upon what we're supposed to find in the second sentence. It says, find the amount of medicine for a child that weighs 54 pounds. And in algebra, whenever we are supposed to find a quantity, we pick a variable to represent it. So we're going to pick a variable to represent the amount of medicine for a child that weighs 54 pounds. So I'll pick X. So I'll read this first part of this sentence again. 13 milligrams of medicine is to 9 pounds of a child's weight, as X milligrams of medicine is to 54 pounds of a child's weight. Well, that particular child weighs 54 pounds, but this is how you can state a proportion in words. So 13 milligrams of medicine is to 9 pounds of a child's weight, as X milligrams of medicine is to 54 pounds of a child's weight. To write that mathematically without the units, we could write 13 is to 9 as X is to 54. So you might agree that writing the equation is a lot simpler than writing out all of those words. You do have to make sure that the numbers are in the right places. In the fraction on the left, the numerator represents 13 milligrams of medicine. And in the other fraction, the numerator has to represent the same kind of thing. And it does, X milligrams of medicine. And the denominators also have to represent the same sort of thing. The denominator on the left, this is 9 pounds of a child's weight. The denominator on the right is also pounds of a child's weight, in particular 54 pounds of a child's weight. Okay, so there's the equation, and all we have to do is solve for X. One technique to use whenever one fraction is equal to another, then cross products are equal. So one cross product is 9 times X. And the other cross product is 13 times 54. So one thing you could do, you could multiply 13 times 54 and then afterwards divide both sides by 9. Or you could notice, well, I'm going to divide by 9, but notice that 54 is 9 times 6. And then I'm dividing by 9. And we can see that one factor of 9 cancels from each. And so X is just 13 times 6, or 78. Okay, then summarize the result. So X is 78 milligrams of medicine. So to summarize this, we could say a child that weighs 54 pounds is given 78 milligrams of medicine. Okay, and that's all there is to it. So proportions, as I mentioned, are fairly easy to solve. You have one quantity is to another as the same sort of quantity is to the same sort of the other, and then you can write the proportion as an equation. Okay, the next problem will be, maybe it will be a little bit more challenging. This one says, Jillian ran 12 miles from her house to the county line, and she got a ride on the return. It took 2 hours longer to run 12 miles than to ride 12 miles. Her run rate was 25 miles per hour slower than her ride rate. So find Jillian's run rate. Okay, what did you get? What sort of equations will we need for this one? So distances are given. Times are given, and rates. So rate times time equals distance is the kind of equation that we're looking at. Uniform motion. Rate times time equals distance, or a variation of that. It could be rate equals distance divided by time, or time equals distance divided by rate. Okay, well, usually if you identify what it is you're supposed to find, that can help you get started. we're supposed to find Jillian's run rate. So let's just pick X to be Jillian's run rate. We're going to assume that it's measured in miles per hour. Okay, so what else do we know now that we have X representing Jillian's run rate? Now what can we say? So a hint is there's another rate besides the run rate. And we're told how the rates, the two rates differ. In the second to the last sentence, her run rate, we're told that her run rate was 25 miles per hour slower than her ride rate. So if her run rate is X miles per hour, what's the ride rate? Okay, her run rate is slower, so X is slower than the ride rate, and it's slower by 25. So if we add 25 to the slower rate, that is X plus 25 miles per hour, this is her ride rate. Okay, now what?
Set up an equation.
Yeah. Yeah, write an equation. Well, let's write two equations. Let's focus on Jillian running to the county line. So I'll just say run to the county line. So let's write an equation of the form rate times time equals distance for the part, or for that case where Jillian runs to the county line. So her rate is X miles per hour when she's running to the county line. We're told what the distance is. The distance is 12 miles. We are not told specifically the number of, or the amount of time it took her to run 12 miles, but we are told that it takes 2 hours longer to run 12 miles than to ride 12 miles. So for now, let's use capital T. I'm going to use this sub run. So X miles per hour times the amount of time it took her to run 12 miles. So this at least gets us started. And then let's write an equation for the ride back. So on the ride back, the rate is X plus 25 miles per hour. And I'm going to write capital T sub ride to represent the amount of time it takes her to ride back 12 miles. Since both run and ride start with R, I thought it would be better to write out the words run and ride. If each one started with a letter different, then I could just use the letter for the subscript. Okay, this is a pretty good start. Now what? Okay, look in the second sentence. The second sentence says it took 2 hours longer to run 12 miles than to ride 12 miles. So that piece of information is going to tell us what to do next. So T sub run, that represents the amount of time it took her to run 12 miles. T sub ride represents the amount of time it took her to ride 12 miles. What are we told about those two quantities? We're told that it took 2 hours longer to run 12 miles than to ride 12 miles. So that means, in terms of our variable assignments, T sub run is greater than T sub ride by 2 hours, right? So from this inequality, we can get an equation. There are 4 equations at our disposal. We only just need one of those 4 based upon this inequality. So is this problem too easy? Am I going too slow? No? Want me to go slower? Okay, this quantity, T sub run, is greater than T sub ride by 2. So one option, the one that I kind of like best, is subtract the smaller number from the larger number and we get 2. So that is the larger number, T sub run, minus the smaller number, T sub ride, equals 2. If they differ by 2, then if you subtract the smaller from the larger, you get 2. Okay. Perhaps I should have, what I'm going to say next, perhaps I should have said sooner, since we're using X to represent Jillian's run rate and X plus 25 for Jillian's ride rate, and we're supposed to find Jillian's run rate, what we want is an equation whose only variable is X. So we're getting close to getting an equation whose only variable is X. We've done some intermediate work. So since T sub run minus T sub ride equals 2, can you see a way that we can replace T sub run with an expression involving only X, and T sub ride with an expression whose only variable is X? It will, of course, use other numbers, but Hey, let's start with this one. X times t sub run equals 12. So that means t sub run, the amount of time it took her to run 12 miles, is 12 divided by x. And in this equation, since x plus 25 times t sub ride equals 12, the amount of time it took her to ride 12 miles is 12 divided by x plus 25. Okay, then by substitution, since t sub run is 12 divided by x, I write 12 divided by x minus t sub ride, but I'm going to replace that with 12 divided by x plus 25. That equals 2. So finally, we have an equation whose only variable is x, and we discussed how to solve equations like this last week. The least common denominator is x times x plus 25. Least common multiple of the denominators is x times x plus 25. So we're going to multiply every term on both sides by the least common denominator. That will clear the denominators, and then we'll have a quadratic equation to solve after that. Okay, with a little practice, you can see what to write down without writing everything down. So we'll do that here. When we multiply x times x plus 25 by 12 over x, the x divided by x cancels, so we'll be left with 12 times x plus 25. And then be careful with the subtraction. But we're going to multiply this term, 12 over x plus 25, by x times x plus 25. This time, the x plus 25s cancel. So we're just left with minus 12x. And we have to multiply the right-hand side by the least common denominator also. When you multiply out x times x plus 25, we get x squared plus 25x. And we're going to multiply that by 2, so 2 times x squared plus 25x. Then we just do some arithmetic in algebra. Multiply 12 times x plus 25. We get 12x plus 300 minus 12x equals 2x squared plus 50x. Uh, 12x minus 12x cancels on the left-hand side, which leaves us with 300. And if we subtract 300 from both sides, we'll just get this equation, 2x squared plus 50x minus 300 equals 0. Note that each of the coefficients and the constant is divisible by 2. And since we're trying to solve an equation, we are permitted to divide every term on both sides by 2, just to get rid of the clutter that's in the way. So when we divide every term on both sides by 2, we get x squared plus 25x minus 150 equals 0. So now all we have to do is solve this equation, x squared plus 25x minus 150 equals 0. So I'm almost out of space. If we use the AC method, 1 times negative 150, so 1 times negative 150 equals negative 150. And we want to see if we can find two integers that have a product of negative 150 and a sum of 25. So if we can find two integers like that, the one with the largest absolute value is 25. Or sorry, the one with the largest absolute value is positive, since they add up to a positive 25. So if you do the exhaustive method, negative 1 times 150, negative 2 times 75, negative 3 times 50, negative 5 times 30. Those add up to 25. Remember the abbreviated AC method that you can use when the coefficient of x squared is 1? Since one of the numbers we need is negative 5, one of the factors is x minus 5. The other number that we need is positive 30, so the factor that corresponds to that is x plus 30. And in the context of this problem, x equals positive 5 is the only solution that makes sense. The other solution is negative 30, but running at negative 30 miles per hour doesn't make sense in this problem. So x equals 5. So Jillian's run rate is 5 miles per hour. So I'll just make note of that. Jillian's run rate is 5 miles per hour. And that's all we were supposed to find, so that's all we will write for that. Okay, if you thought that was sort of challenging, or if you found that you didn't really know how to go about it, make sure that you practice as many of those problems as you can. Okay, the next problem. This one says, James can plant a garden in 8 hours. But if his daughter helps, the two of them can plant the garden in 6 hours. Find how long it would take James's daughter to plant the garden by herself. Okay, so an underlying assumption that we're going to make, which might not be true in real life, is that both James and his daughter work at the same rate all the time. Hey, what kind of problem is this? Or what kind of equation do we need? This kind of equation is sometimes referred to as a work problem. And equations in work problems have the form rate times time equals 1, where 1 represents the job that they are, or the task they are completing. So in number 3, the one job that they are working on is planting a garden. And it seems to make sense. If you work at a certain rate for a certain amount of time, you will plant one garden. Okay, so we're told that James can plant one garden in 8 hours. So for James, we can write down an equation, rate times time equals 1. So for James's rate, I'm going to write R sub j, and his rate times 8 hours equals 1 garden planted. So this means James's rate is 1/8, but that's just an informal way of saying what his rate is. What's a little bit more formal way to say what James's rate is? Well, this just means that James can plant 1/8 of the garden per hour. So it might help to know it might help you to remember if you know what it is that you're doing. So this is like saying James can plant 1/8 of the garden per hour. That's his hourly rate. Hey, if his daughter helps, the two of them can plant the garden in 6 hours. So let's write an equation for the daughter, rate times time equals 1. We're supposed to find how long it would take James's daughter to plant the garden by herself. So let's refer to her rate as R sub d times capital T. We don't know how much time it's going to take yet. That's what we're supposed to find. So we assign a variable to represent the daughter's rate. And so the daughter's rate is 1 over capital T. If they work together, we're told how long it takes them when they work together. When they work together, the overall rate is James's rate plus the daughter's rate. And we're told that when they work together, they can plant the garden in 6 hours. So James's rate plus the daughter's rate times 6 equals 1. So that means James's rate plus the daughter's rate is 1/6. So in other words, when they work together, they can plant 1/6 of the garden per hour. So what do we need in order to solve for t? We need an equation whose only variable is t. And we have all of the subcomponents necessary to get one equation whose only variable is t. We know what James's rate is. James's rate is 1/8. He could plant 1/8 of a garden per hour. So in this equation, we're going to replace James's rate with 1/8. The daughter's rate, we're using 1/t to represent that. So we have 1/8 James's rate plus the daughter's rate, 1/t. When they work together, the rate is 1/6. So here is our equation whose only variable is t. This is an equation with rational expressions, so we know how to solve equations with rational expressions. So let's find the least common multiple of the denominators, least common denominator. The three denominators are 8, t, and 6. If we first find a common multiple of 8 and 6, then after that we can just include the factor of t. The multiples of 8 are 8, 16, 24, 32, 40, and so on. The multiples of 6 are 6, 12, 18, 24, 30, 36, and so on. So the least common multiple of 8 and 6 is 24. And then 24t is also a multiple. So 24 times t is the least common denominator. And so we multiply every term on both sides by 24t. Uh, 24t over 1 times 1/8. 8 goes into 24 3 times. So this simplifies to 3t. 24t over 1 times 1/t. The t's cancel, so we get 3t plus 24 on the right-hand side. 24t over 1 times 1/6. 6 goes into 24 4 times, so we get 4t. And then we're just one step away, subtract 3t from both sides. And we get t equals 24. So to summarize this, we would just say it takes James's daughter (24 hours) to plant the garden. Okay, let's start the next one. Number 4. Jenna flew 1,080 miles in a jet, and then she drove 240 miles in a car. The jet traveled 300 miles per hour faster than the car, and the car ride was 1 hour longer than the jet ride. Find the speed of the car. Find the speed of the car. So we pick a variable to represent the speed of the car, any variable you like. I'll just pick x. The jet traveled 300 miles per hour faster than the car, so we can write down an expression for the jet speed. That will be x plus 300 miles per hour. Okay, so now what? Well, we're told the distance flown by the jet. 1,080 miles is the distance flown by the jet. The distance driven in the car was 240 miles. And then we're also told that the car ride was 1 hour longer than the jet ride. So let's write an equation for the jet ride, and then another equation for the car ride. And then we'll use the information about how much longer it took in the car, the car ride was than the jet ride. Okay, so the jet ride, we want rate times time equals distance. So the rate for the jet, we're using x plus 300 miles per hour. And we'll use t sub j for the amount of time it took the jet to fly 1,080 miles. And then the car ride, the speed when driving the car was x miles per hour. And it took a certain amount of time. We'll call it t sub c. And the distance traveled by the car was 240 miles. Okay, so what do we do with this information? The car ride was 1 hour longer than the jet ride. That is going to be a key to getting an equation whose only variable is x. Okay, the car ride was 1 hour longer, so that means t sub c, the amount of time it took to drive 240 miles, is greater than t sub j, the amount of time it took to fly 1,080 miles. It's bigger by 1 hour. So we can get an equation from this inequality. So the larger number, t sub c, minus the smaller number, t sub j, equals 1. So if we solve this rate times time equals distance equation for time in both cases, then we can use substitution and get an equation whose only variable is x. So let's solve the top equation for the t sub j. The amount of time it took the jet to fly 1,080 miles is distance divided by rate. And the amount of time it took the car to travel 240 miles is the distance 240 miles divided by the rate x. Okay, and so our equation, the amount of time it took the car to drive 240 miles minus the amount of time it took the jet to fly 1,080 miles equals 1. So by substitution, we get 240 divided by x minus 1,080 divided by x plus 300 equals 1. Okay, so finally we have an equation whose only variable is x. It's an equation with rational expressions. So the least common denominator is x times the binomial x plus 300. We multiply every term on both sides by the least common denominator. When we multiply the least common denominator by 240 over x, the x's cancel, so we get 240 times x plus 300. And then multiply the least common denominator by 1,080 over x plus 300. The x plus 300 binomials cancel, so we get minus 1,080x. And then on the right-hand side, we're just going to multiply 1 times the least common denominator. When we multiply x times x plus 300, we get x squared minus 300x. Here we get a quadratic equation. The numbers look pretty big, but with your high-powered calculator, you can do this pretty fast. So let's multiply 240 times the binomial x plus 300, so we get 240x plus 72,000 minus 1,080x equals x squared minus 300x. Okay, so on the left-hand side, the 240x minus 1,080x is negative 840x. And then we're going to add 840x to both sides. Let's make the left-hand side 0. So we're going to add 840x to both sides. So the right-hand side will become x squared plus 540x. And then we're also subtracting 72,000. So here's our quadratic equation. The numbers are kind of large, but I'll leave the rest of that for you to do. Using the AC method, 1 times negative 72,000, find two integers that have a product of negative 72,000 and add up to 540. One hint or one thing that you can do to avoid using unnecessary integers, well, if two numbers have a product that's negative 72,000, this number has 3 zeros on the end, and if they add up to 540, you can limit the x or the numbers to multiples of 10. Right, you don't have to start with 1 times, or negative 1 times 72,000 and 2 times 36,000. You can use larger numbers like 10, 20, 30, and so on. And it won't take too long to figure out what those are. Okay, but we're about out of time. Tomorrow we're going to do more of the word problems. So on the sheet that on the notes that I sent yesterday, we still have 4 more problems to do. If we get done with those, I'll have a couple of others that I'll do after those, if we get done with the next 4 tomorrow. But that's all for today.